Welcome back, and it is now officially the last podcast of this semester for chemistry, which is kind of crazy. So, guys, we still have another week after this week 11. Your week 12 is going to be your entire course review assignment. And just so you're aware, there aren't going to be new podcasts for that week, but I will present the opportunity for various Google Meets in the days of that week in order for you to optionally join in to get a little bit of help, especially considering it's stuff you haven't done in a while. So do keep that in the back of your head as we continue forward. And like I said before, I really encourage you to get this week 11 assignment done and in on or before that Monday, June 15th, just to allow yourself the full week to work on that final assignment. Okay, here we go. We're now going to go on to actually figuring out some calculations related to acid-base titrations, which directly relates to the equivalence point. So equivalence point, guys, to remind you again, is the volume of the titrant that's added out of the burette, which means if it's a volume, it's a numerical value, it's a number of milliliters. So that's something that we can start to analyze stoichiometrically. Here we go. Now, ultimately, we can do one of two things here. We can either add an acid titrant to the base aliquot, or we can do the opposite. We could be adding a base titrant into an acid aliquot. Ultimately, though, it's an acid and a base. Now, what we do at its most simplest in grade 11 titrations is we're dealing with equal moles of reactant acid and base combining. And we call those monoprotic acid-base reactions, which basically means, guys, it's a fancy way of saying, hey, your mole ratios are going to be 1-to-1, which makes them quite lovely and quite easy. Now, potentially with some of the bases that end up reacting, you could end up with a 1-to-2 ratio as well. And if that happens, I just want you to pay attention to the balanced reaction. It's the same stoichiometric type stuff that we've been doing the last 2 weeks. It's just that the data is coming from an experiment rather than from me just giving it to you in the question. That's really the only difference. And because it's coming from an experiment, there's some terminology and some process of how we analyze experimental data that's slightly different from last week or the week before. So, going back to that acid-base reaction, an example of a type of titration you might have is this one. We might have hydrochloric acid reacting with sodium hydroxide. And let's say for this scenario, we have 10 milliliters as the aliquot of hydrochloric acid. So each Erlenmeyer flask has 10 milliliters of HCl in it. And we would have the sodium hydroxide then in the burette. So we would slowly let the sodium hydroxide drip, drip, drip into the Erlenmeyer flask contained with the hydrochloric acid, and we would stick an indicator into the Erlenmeyer flask with the HCl, and when that indicator changes color, bingo, we know that the reaction is complete. That is the ultimate way a titration works. Okay, now, like I mentioned before, in this scenario, we have a mole ratio of 1-to-1. So that means that equivalence point occurs when an equal amount, and by amount, guys, remember what amount means in chemistry. An equal number of moles, right? That's what amounts are, of hydrochloric acid has been added to the NaOH, right? So in other words, if you started with 2 moles of hydrochloric acid, you're going to add 2 moles of sodium hydroxide for it to fully react. The cool thing about reacting strong acids with strong bases is we end up with the reaction being finished, so the equivalence point occurring at exactly a pH of 7. And this is super logical. Ultimately, you have a situation where all of the hydronium ions, the H3O plus, have reacted with all of the hydroxide ions, the OH negative, and think about what that means. All of the hydronium react with all of the hydroxide. What do those two things become when they react together? Oh, they become water, of course. So if that's the case, what's the pH of water? 7. That's how we know it's been neutralized. So if we can simply find an indicator that changes color right about 7, beautiful, we're good to go. And just a side note, a good indicator for that is bromothiamyl blue. Turns green, right at a pH of 7. Perfect. All right, let's keep going. This is another part that relates directly to the experimental aspect of a titration. Titrations are dependent upon having something called concordant results. Now, the word concordant just means close to the same. They don't have to be identical, but they gotta be pretty good. So we say for titration specifically that if you can get 3 results in a row that are really close to each other, then that's a good titration. You have enough data to analyze in order to get a valid answer, a valid concentration. And in terms of those concordant results, we're specifically saying that you're going to get 3 volumes coming out of the burette that are within, right? Here's your burette. It's going into the Erlenmeyer flask, right? With the aliquot in it. Those volumes need to be within 0.2 milliliters of each other. I'll give you an example. If I have my first volume is 8.0 mils, and I have my second volume is 8.3 mils, you would look at those and be like, yeah, that's pretty good. But I would come by you when you're in the lab and say, no, not good enough. Do it again. Be like, why? It was good. It's like, no, it's not within 0.2. Those are within 0.3. So like, fine, I'll do it again. And let's say this time you got 8.4 mils. You'd be like, yeah, I did great. I would go over to you. I'd be like, you know what? You did do well. 2 of those are concordant. This one and this one are within 0.2 of each other. But do it again. You don't have enough. So then you're in the lab again and you're going through it, and you get 8.6 mils. You're like, yeah, I got it. And I would come up to you and say, no, it's not good enough. Because, 8.6 is within 0.2 of 8.4, but it's not within 0.2 of 8.3. It's not 3 results within 0.2. So once again, you're doing it again. So now we're on the 5th trial of doing this titration. And you do it again, and this time you get 8.4 again. Woo-woo! Nicely done. You just got 3 concordant results. You can now be finished your titration. Okay? And ultimately that means the 8.0 and the 8.6 weren't good enough. This one took you 5 trials. I've had students sometimes have to take 8 or 9 trials because they're just having issues. I've had other students that pull it off in 3 trials, right? It just depends on how carefully you are allowing the drip, drip, drip out of the titrant from the burette into those aliquot samples in the Erlenmeyer flasks. Okay. So here's an example. Let's say this is data that someone got from doing a titration. And what I want you to do is figure out the equivalence point for every trial. And look at that word equivalence, right? It's got a V in it. And that helps you to remember that we're dealing with the volume, right? That's what equivalence point is about. It's about a volume amount for when the reaction is to completion. So for each trial, this person had 5 trials. The first one is just a really rough one, so probably not good data, and then 4 more good ones afterwards. And then we're going to calculate something called the average volume. Get used to this. You're going to have to do it a lot. So let's begin by just writing down beside here that underneath we are going to find the equivalence point of each of these. If my pen would work, a lens point. Now each of these guys is in mils, just to clarify, including the initial volume and the final volume on the burette. Okay, here we go then. How do you do this? Well, it's a pretty simple process, guys. All we do is we take the final volume minus the initial volume. And that's all it is, right? So volume equals VF minus VI. And this one would have been done with a 50 milliliter burette. So the great big burette, long piece of glassware, would have had increments. It starts with 0 at the top, ends with 50 down here, and you slowly drip the titrant out that's inside, okay? It's usually not pink, by the way, the titrant. Usually it's just a clear, colorless solution. So first time when we do this, 15.7, I'm under the rough, minus 0.0. The difference between those is 15.7 mils. Fine, done and done. Now I'm going to go to trial 1. I've got 30.6 minus 15.7. Simple number crunch in your calculator, 14.9 mils. All right, done. Next trial, 45.7 minus 30.6. That is 15.3 mils. We definitely don't have concordant results yet. Now notice something. When we're at 45.7, honestly, that would be when you're getting really, really low in your burette, rather. You're literally down to the very, very close to the bottom. So there's almost no solution left in there, right? We're way down here. So at that point, we refill the burette so it's right to the top again. That's why the next value is close to 0, right? It's right full. So keep going. 15.3 minus 0.2, I get 15.1 mils. Do the last trial, 30.5 minus 15.3, 15.2 mils. All right, analyze them all. Which ones are concordant? Sure enough, we end up with these last three that are within 0.2 mils of each other. So we scrap those two. We just don't use them. And these, by label, are your three concordant results. Now, how do you take those and figure out what the average volume is? It's pretty logical. We would say VAV is equal to, now remember, averages are found by adding everything together and then dividing by how many you have. Well, in this case, I've got three different entities, three different volumes, 15.3 plus 15.1 plus 15.2. And I put those in brackets, then I can put the mils on the outside. Divided by, there's 1, 2, 3 different things, so I divide by 3. That means that my average volume is equal to 15.2 milliliters. Done and done, guys. There is average volume. This is an extra step that needs to happen in many of your titration questions, especially when you are given a table. And if you were in the actual lab performing one, it would be those equivalence points that you would be finding the initial volumes, final volumes, right? Subtract them. That's what you'd be doing in the lab. You'd be seeing the reactions to find out when it's complete by a color change and recording the data. Hence, quantitative data, quantitative analysis. Numbers. All right, let's keep going. I want to clarify again those two different words, your equivalence point versus your end point. So I mentioned those in the previous podcast. Ultimately, endpoints are all about color changes, right? It still tells you when the reaction is complete. That doesn't change, but it's about a color change. Vice versa, the equivalence point is all about when enough volume of titrant has been added for the reaction to be complete. So I'll say it again. They both relate to the completion of the reaction. Totally do. But endpoint is a color change, whereas equivalence point is a numerical volume amount of titrant added. Happen at the same time, represent two different specific characteristics of the reaction being complete. Alrighty, from an indicator perspective, when you add an acid-base indicator to a solution for a titration, you're getting something that changes color over a specific pH range. And this is actually a type of what we call equilibrium reaction, that when we have the acid form of the indicator, it's one specific color. And when we have the base form of the indicator, it's going to be a different color. And that's the biggest characteristic, is that they have to be distinct. Now, I mentioned already that bromothiamyl blue, and that's a great indicator to use, especially when you're dealing with a strong acid like hydrochloric acid and a strong base like sodium hydroxide. It's yellow when it's less than 6 pH. It's blue when it's greater than 7, basically, 7.6. So if we have a pH right at 7, it's a perfect green color, definitely a good color change, easy and useful for neutralization. Whew. Let's get into an example. Now, this is an example of a titration where I'm not giving you a chart. So that makes your life a little bit easier. Here's some of the information you're given. You're told that 20 milliliters of hydrochloric acid is being used. So that means you've just been given the volume of hydrochloric acid. Think about what that means. If you've been told that's the volume of hydrochloric acid, Where is it? Is it in the burette, or is it hanging out in the Erlenmeyer flask? Well, it has to be in the flask. Why? Because that's where measured volumes go. With a volumetric pipette, you would carefully measure 20 mils of hydrochloric acid and put it into the Erlenmeyer flask. Okay, let's keep going. Then the next thing that we do is we have some sodium hydroxide. And this sodium hydroxide has a specific concentration. The sodium hydroxide, we don't know the volume of yet. It's put in the burette. So it is the sodium hydroxide that is in this long piece of glassware that we can carefully control how much we get. So here's the sodium hydroxide in here. And then the question says, hey, the initial reading of that burette is 0.20 mils. After we let a little bit out, the final reading on that burette is, that's quite a bit lower. It's way down here by the end, right? 36.0 mils. This number there. So that means this whole portion has been dripped out into the hydrochloric acid. How do we know how much that is? Well, you got to calculate it. So let's go with that then. The volume of the NaOH that we're going to actually end up reacting is going to be the final volume on the burette minus the initial volume of the burette. In other words, it's going to be 36.0 mils minus 0.20 mils. Okay, fine. Subtract those two. We're going to end up with a total of 35.8 milliliters. Don't worry about significant digits at this point, guys. We'll figure out the significant digits at the very end of the question, and then we'll be good to go. Okay, so going through this again, let's continue. That's our volume of our sodium hydroxide. But what does that mean for actual stoichiometry? Well, at this point, guys, we really can't do this question. Let's set up a reaction first so that we can truly see what's happening. It's an acid-base reaction. It's sodium hydroxide reacting with hydrochloric acid. So let's put it together. Sodium hydroxide reacts with hydrochloric acid to produce, and it's going to be a double replacement reaction, a neutralization, it's a special one. We get sodium chloride when the sodium and the hydrogen split apart. And then we get water, of course, H2O. Same thing as HOH, if you will. Okay, there's our reaction. Now let's put down what we know. So going through the question, I know that I've got 20 mils of the hydrochloric acid. Okay, fine. So I've got 0.02000 liters, or I'm going to convert it into liters. And the concentration of the hydrochloric acid, I'm not sure. And look back at the question. That's the whole point of what we're doing. What is the concentration of the hydrochloric acid? What is the concentration? I'm not sure. Let's keep going. Okay, continue to write down what givens we have. Sodium hydroxide, we just figured out what the volume is, 35.8 mils. Divide that by 1,000. We're going to have a volume equal to 0.0358 liters. Now it's in liters. Remember in the question, we were given the concentration of the sodium hydroxide. It's 0.1000 moles per liter. Okay, look at this thing. What can we do? Well, go back to the point of the question, the concentration of the hydrochloric acid. We have a balanced chemical reaction here of hydrochloric acid, which is in the Erlenmeyer flask, reacting with sodium hydroxide that was dripped in from the burette. We know exactly what volume of sodium hydroxide was required. We figured it out by what dripped out of the burette. So let's use that volume and concentration to figure out the number of moles of sodium hydroxide. N equals C times V. 0.1000 moles per liter concentration times the volume, 0.0358 liters. That's what dripped out of the burette. We took the final volume minus the initial volume of the burette. We're going to get a total of 0.00358 moles. All right. Now that's the moles of sodium hydroxide. We need to relate this to our moles of hydrochloric acid. How do we do that? Yeah, well, with the mole ratio, of course. So let's go through it. Our HCl compared to our sodium hydroxide, good news is balanced reaction. These are a 1-to-1 ratio. That's nice and easy. So what amount of hydrochloric acid reacts is 0.00358 moles of sodium hydroxide. Oh, the math really couldn't get any easier. We're going to have 1 mole times 0.00358, and then we're going to divide by another mole. Easy peasy, guys. In other words, we will end up with N over here of our HCl that's exactly the same. 0.00358 moles of hydrochloric acid. Look how close we are. We've got the volume of hydrochloric acid. We've got the number of moles of hydrochloric acid. We have everything that we need now to figure out the concentration. C is equal to N over V. Plug in what you know. 0.00358 as determined by that 1-to-1 mole ratio divided by 0.02000 liters. Number crunch, and officially our concentration of hydrochloric acid is equal to, now we'll go to our question which has 3 sig digs, so we'll go with, I see I've got 2 sig digs up there with my 0.20, except when we subtract and I got 3. So no, 3. Sorry, thinking out loud. 0.179 moles per liter. Dun, 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 dun. And there you have it. Concentration of the hydrochloric acid found from a titration. Okay, you'll have a few questions like that, very, very similar, that you need to do in the assignment, but you'll also have a good chunk of questions that look like this. Where you're given a chart, and now you got to figure it out. Now, here's where things get interesting. The whole point of this question is to figure out the concentration, right, square brackets, of sodium hydroxide. That's what it actually says on your sheet. What is the concentration of the sodium hydroxide? Now, when you see questions like this, guys, one of the most important things that you need to do, that a lot of people don't, is pay close attention to the title of the titration observation table. And when so many people miss this, is that they don't recognize that there's really pertinent, important info in there. For instance, we're told in here that it's 10 mils of sodium hydroxide. Well, that's extremely useful. And we're told the concentration of HCl. So there's 2 things that you just got out of this. Number 1, you got the reactants, sodium hydroxide and hydrochloric acid. That's huge. Second thing you got is specific quantitative measurements about the sodium hydroxide and the HCl. Now, here's one mother hint. You're told that this is the volume of sodium hydroxide. If you already know the exact volume, then guaranteed it is the sodium hydroxide that's sitting in that Erlenmeyer flask. That is a horrible picture. Let's see if I can draw that a little bit better. No, it's not much better. Oh well. Okay, so it is then my sodium hydroxide that's sitting in there. How much of it? 10 mils. All these volumes, initial burette volume, final burette volume, that's of the hydrochloric acid that's getting slowly dripped into the sodium hydroxide. So drawing-wise, this is going to be yellow, right? Just so you can kind of combine those different colors together. All right. So if this is the case, then we need to figure out what the equivalence point was for each trial, and then figure out what the average volume of HCl added was. Again, how do I know it's the HCl that relates to these equivalence points? Because I'm specifically told that the sodium hydroxide has 10 mils, right? I know it's in that Erlenmeyer flask. All right, let's do some number crunching. Really simple stuff, guys. Final volume minus initial volume. Literally, subtract them. Plug them into your calculator. No big deal. I'm going to go through these really quick. 10.5, 8.8, 8.6, 9.0. Literally, subtract. Easy peasy. 8.7 and 8.8. Next step. We look at all those different volumes and we need to figure out the concordant ones. Now I'm going to say this a little bit differently. We need a minimum. So that's the lowest number of 3 concordant results. What if we have more than 3? Should you use them? Yeah, that means a more accurate calculation. Why wouldn't you use more? It's kind of like saying that, are you just going to use 2 of your tests, not all of them? No, we use them all. Okay, so all of the concordant ones. So I'm going to use 8.8 and 8.6. Those are within 0.2. I'm going to use 8.7 and 8.8. All 4 of those are within 0.2 mils of each other. These 2 are considered to be not good enough data, such as life. Let's figure out what our average volume is going to be. So we take it, say VAV is equal to, and write down all of the different volumes. 8.8 plus 8.6. Yes, show your work, please. Plus 8.7 plus 8.8. They're all in mils, so I'll put that out of brackets. Divide it by 4 because there's 4 different volumes. Don't round this, guys. We're going to have to use it again. It is 8.725 mils. Now, what this equal to is your average volume of hydrochloric acid. Why of hydrochloric acid? Because that's within the burette. Because the given volume of 10 mils must be of the sodium hydroxide. All right, we need to continue. I'm going to flip over to the next page. Hopefully you've got that volume written down because we're going to have to use it to write down our given values. You're also going to need the different values in your table. So next step is we need a balanced chemical reaction. Same reaction as we used in the previous example. Sodium hydroxide is reacted with hydrochloric acid. It is a double replacement reaction. Sodium and hydrogen are going to switch spots. We end up with sodium chloride, aqueous, because it is highly soluble, and water. That hydrogen goes with the hydroxide, the OH, water's formed. Okay, write down your givens. Once again, we are told that you've got 10 mils of sodium hydroxide. Divide that by 1,000 and we can convert it into liters. The whole purpose of the question was to find the concentration of sodium hydroxide. We don't know. Go to the hydrochloric acid. We just found from the table the average volume of it. That's what we need. Keep in mind, though, I outlined it in red here, 8.725 mils. You got to divide that by 1,000. Put it into liters. So then we have 0.008725 liters. The concentration of the HCl is also given to you in the question. It's 0.10 moles per liter. All right, there we go. There's our given info. What do we do now? The whole purpose is to get the concentration. Guys, you've done questions like this. This is just solution stoichiometry. The difference is where you got the data from. That's why it's new. So ultimately, if we've got C and we've got V, we can find N for the hydrochloric acid. N equals C times V. Let's plug in what we know. 0.10 mole per liter times the volume, 0.008725 liters. Liters cancel out. We're left with a number of moles of 8.725 times 10 to the negative 4 moles. Alrighty, how do you use this? Well, you stop and you look at this and you go, oh, look, we have a mole ratio. It's a balanced chemical reaction. The number of moles of sodium hydroxide compared to the hydrochloric acid is a 1 mole to 1 mole ratio. And then this we can find from that X, knowing that the moles of HCl is 8.725 times 10 to the negative 4 moles. Cross multiply, divide, it's 1 to 1, guys. It doesn't get any easier than this. And then we know we have X equal to the same number, 8.725 times 10 to the negative 4, which is equivalent to our moles of sodium hydroxide. All right, we're in good shape now. If we now know the number of moles of sodium hydroxide, right, 8.725 times 10 to the negative 4 moles, and we already had the volume, if we've got N and we've got V, we're golden. We can find C. And that's the whole point of the question. C equals N over V equals 8.725 times 10 to the negative 4 moles divided by that volume of 0.0100 liters. Number crunch away, and we need 2 sig digs as dictated by the 0.10 mole per liter HCl. So our answer is 8.7 times 10 to the negative 2 moles per liter. And there you have it. That is our official concentration of sodium hydroxide. All figured out by a quantitative analysis of titration data. Whew! All right, you are now officially ready to finally get into the assignment. And you can do a lot of it. You can do questions 1, 2, 3, 4, and 5. And honestly, that's over half of the assignment done. Even though it's 2 pages in and it looks like you have a whole bunch of pages left, the lab really doesn't take that long. The lab itself to watch is about 7-8 minutes, and some of the questions are extremely easy. They're basically just taking it right down off the lab, copy it down, good. There's 2 titration calculations involved in the lab, and that'll be a little bit more, right? So the lab that I'm referring to, guys, is this titration procedure to determine the concentration of a base, right? So make sure you do these 5 questions first, then watch the lab, and then you can finally go and complete questions 1 to 13 in that lab investigation. There we have it, guys. The end of new material of Chemistry 20. You have, once you do this, officially completed course content for this distance learning, which is kind of crazy. It's been an interesting ride, folks. Make sure if you've got questions that you ask, please email me. Come to the optional Google Meet on Thursday. I'm here to help you, and I hope to talk to you all soon. Take care.